Hi guys, we're going to talk about exponential growth and decay today. So exponential growth, a few things. It's going to be an increasing function, meaning the graph is going to rise as we move left to right, and it's going to model a situation that is increasing by the same percent over a time interval. So here's an equation. F of x is equal to a times b to the x power. A is always your initial amount, and b is the percent that it's changing each time. We are going to be given a rate of some sort, and we have to add 1. That plus 1 just indicates that it's an actual growth. A has to be greater than 0. You can't have an initial amount less than 0. And then because it's growth, our b value will have to be greater than 1 also. A real-world application that is used a lot of times is calculating interest of money in a bank account. So we will use that formula. We've seen that in lesson 47 also. Few things about exponential decay. So it's a decreasing function, meaning that the graph is going to fall or decrease as we go left to right. And then this is going to model a situation that decreases by the same percent over each time interval. So same formula this time. A is obviously still our initial amount. This time our b value has to be between 0 and 1. So we're going to take 1 and subtract the rate that we're decaying at. Okay. So now in any decay problem, our b value will always be between 0 and 1. An example in real life would be like if you take any sort of medicine, that medicine will decrease, the amount left in your body will decrease over time. So that's an exponential decay. Another one is like the value of a car. Once you buy it, it exponentially decays the longer you have it. So we're going to do an interest problem. So this just gives you some information. We have a savings account that has an interest rate of 4%. It's compounded quarterly. We have a principal amount of 1,000, and we're $1,000, and we're wondering how much will be left or how much will be in our account after 3 years. So we use this formula that I mentioned on the first set of notes. P stands for principal, so we're going to plug 1,000 in there. That 1 plus is just showing that it's going to be a growth problem. R is our rate, our interest rate as a decimal, so that'd be 0.04. N is the number of times it compounds in a year. Well, quarterly means that we would compound interest 4 times. Use that same N value here, and then T stands for time. So plug all of those numbers in, do the calculations, and you get that we would have $1,126.83 after 3 years. Okay, here's just a little about compounding. There's the different options. You can do annually, semi-annually, quarterly, monthly, and daily are the most common ones. So there are your N values for each of these. After daily, though, we really jump to continuous compounding. So the more times you compound in a year, the more money you're going to have. We don't generally do, like you could, I suppose, do hourly, but generally we just go from daily to compounded continuously. And here is the continuous compounded formula. So we're going to use that. It says savings account has an interest rate 4% compounded continuously, starts with 1,000, how much after 3 years. So similar to the problem we just did, using our compounding or continuous compounding formula, plug our numbers in. Remember, E is just on your calculator. You have $1,127.50. So compared to our last example, we had that much money. Here we have a little more. So the more you compound, like I said earlier, the more money you will have in your account. Okay, this question's still a bank account question, but it asks for you to solve for a different piece of information. So we have 3.5% interest compounded continuously. After 5 years, our amount is $3,200. We need to figure out what is that original principal. So compounded continuously tells us we're going to use this formula. Plug our numbers in. This time we have $3,200 in the end. We don't know that principal. This is still something you can type into your calculator. So when we do that, it's roughly this 1.19 decimal. Divide, and it says our principal, or the amount we started with, was $2,686.26. So to go back to our original or our general formula for exponential growth and decay, we're going to work on building equations that don't have to deal with money. So just a couple things to keep in mind. X generally is going to indicate some sort of time interval. And then our Y is going to represent the total amount after our given time. So we're going to look at an exponential decay problem. So it says the element nobelium has a half-life of 58 minutes. Write an exponential equation to find the portion left after X minutes. And then the second part says find what percent is left after 15 minutes. So this, it says half-life, meaning that our amount of this element is going to be decreasing. So that's what indicates it's a decay problem. We know we're going to have y equals a times b to the x because it's an exponential. We're consistently decreasing by a half each 58 minutes. So we're going to assume we're working with one element of nobelium to begin with. So if a is equal to 0, we can simplify our equation to y equals b to the x power. Now, since we know it's a half-life from our equation before, we take 1 minus our rate. Well, our rate is 0.5, so 1 minus 0.5 or 1 minus a half gives us b to equal a half. Now, our power, we know talks about time. Well, our half-life happens every 58 minutes, so we have to take however many minutes we're given and divide it by 58 to see how many half-lives we have. So this itself would be our equation, the exponential equation. And then the second part of the question asks us to find what percent is left after 15 minutes. So we're going to take 15, plug it in for x, because remember up here we talked about that x generally represents time. So we plug 15 in here. Again, calculator problem, 1/2 to the 15 over 58's power gives you roughly 0.835 ish. So we round that to we have roughly 84% of our nobelium left after those 15 minutes. Let's do another one. This time we have information given to us in a table. So we're talking about pendulum and the swing of the bar of the pendulum. So we're given different amounts of swings and how far in meters the pendulum goes. So our goal is to write an exponential equation. Again, there's our general form, y equals a times b to the x. This time we know that our initial value, our a value, is 2.17. So we can automatically substitute that in to get y equals 2.17 times b to the x. Now, we don't know our b, but we have enough information to solve for b. So to solve for b, we're going to plug in this next column into our equation. Okay, this time x stands for the number of swings and y stands for the distance in our meters. Think of this as an xy table. Okay, so after 3 swings, our swing is 1.5 meters. We can solve this for b. We start by dividing by 2.17 on both sides, and then we take the cube root to undo that cubed power. So 1.5 divided by 2.17, and then the cube root gives us that our b value is roughly 0.88. So we're going to take that 0.88 and plug it back in here for b. Our exponential equation for this decay problem is y equals 2.17 times 0.88 to the x power.